Hey everyone, welcome back to another episode from the Waste Tutor. This is video 9 of the functions topic, and it's basically going to be unifying all those functions that we've dealt with in the previous couple of videos into a unified definition of a function. So if we move into the overview, we can see that this is the functions topic specifically, so it's dedicated to understanding what a function is conceptually, and so the first thing I'm going to do is I'm going to define what a function is, then introduce function notation, which I might have already used in a couple of the previous slides, but I'll be introducing that formally now. I'll be talking about domain and range of functions and recognizing independent and dependent variables, as well as understanding what the concept of a graph of a function is. And we've dealt with a bunch of graphs in the previous video. For example, we dealt with trigonometric function graphs. Then we're going to move over into transformations. So we deal with translations, both horizontal and vertical. We deal with dilations and reflections, both horizontal and vertical as well. And this is going to be something you've seen and hopefully can relate to in the previous videos. Finally, we'll have a look at the distinction between functions and relations. So functions are, well, we'll have a look at that, and we can distinguish between functions and relations using the vertical line test. So let's get started. Okay, so the first thing I want to do is to come to a conceptual understanding of what a function is. What a function is it's essentially a machine that takes some kind of input and converts it into a corresponding output. For example, let's say you have an input that is will represent by a square, and this is your input. You feed that into some machine, this being your function, and it spits out some output. And the important thing is that each input will correspond to a unique output. That is, a function does a specific set of transformations to that input that converts it into a unique output. If you were to put anything else into this function, it would result in a different output. And one input can only correspond, or more specifically, one input can only correspond to one output. You can't put the square in and expect a triangle in one case and a circle in another case. It will always be a triangle. So in terms of a function, essentially what happens is a function can be written, we've kind of looked at functions already in terms of quadratic functions, trigonometric functions, and linear functions. And essentially what it is, it's linking one variable to another variable. And in the case that we were dealing with, we were looking at y being related to the variable x in some way. This is an example of a linear function. In this case, the output is the same as the input. You can also have y equals cos x. In this case, our function of x is the cosine function. We have y equals sine x, where sine is the cosine function. Sine is the function of x here. And if we look at introducing function notation, we can also write all of these y's as functions of x, where in the first case, our function of x is cosine x. In the first case, our function of x is x. In the second case, our function of x is cosine x and sine x, for example. So these are all examples of functions of x. Importantly, when it comes to a function, they have an associated domain and an associated range. So in the case of this function x here, we have a domain which is all the values that x can assume. This is our domain of x. And those values, every single value in this domain of x, will map to a corresponding y value. And that corresponding y value is the output. It is the range of values that x can assume. Okay? And so in the case of our square maps to a triangle. We could have a circle that maps to a pentagon, let's say. The important thing is that each value in this range only has one component of the domain heading toward, each component in the domain will only map to one corresponding value in the range. So in this sense, it's a mapping of what your domain is onto a range. In the case of your function y equals x, the domain of the function y equals x is x can assume any real number. And the range of x is that y can also assume any real number. If we look at cosine x though, for cosine x we know that x can assume any real number. However, the y value is bounded by -1 up to 1. So our range of x, or our range of y, is equal to y is an element of R, where y is bounded between -1 and 1. Okay, so we've had a look at domain and range now. In terms of dependent and independent variables, our dependent variable is our output, and our independent variable is our input. And the reason why that's the case is that our dependent variable depends on what is put into the function. And so commonly, our most common dependent variable is y, and our most common independent variable is x. The last thing I'm going to do in this slide is have a look at the concept of a graph of a function. When we're looking at graphs of a function, essentially what we're doing is we're putting down, we've basically already looked at this several times, but we're looking at each x value and what y value that x value maps onto. In the case of y equals x squared, we know that for every x value, y is equal to the squared of that. 1 is corresponding to 1, 2 is corresponding to 4, and so on and so forth. And so we have a function that connects all these points like this, like this. And so this is the graph of a function of x. More specifically, the function f of x equals x squared. And we can write this as f of x or y if we wanted to, and we can write this as x if we wanted to adopt the function notation. Next, let's take a look at translations, dilations, and reflections. So when it comes to transformations, more broadly, these are all examples of transformations. There are three types. There are translations, there are dilations, and there are reflections. And reflections, realistically, are kind of like a subset of dilation in terms of what you do algebraically to the function. So if we look at translations first, translations can either be horizontal or vertical. I'll deal with vertical translations because I think they're more easy to wrap your head around. So in the case of a vertical translation, what happens is you take your function and you move it a couple of units up. In this case, we're moving the function k units up, or in the positive y direction. So if we had an initial function that looks kind of like this, then we would be mapping this function k units up, and so each corresponding value of y is k units above where it was initially. In the case of a horizontal transformation, this deals with moving a function right or left. So we look at it like f of x take c, for example. If we look at our function, if we look at a function like this, for example, and we wanted to move it over, then the f of x minus c will actually move it to the right, c units to the right. And so each value that was initially there has now been moved c units to the right. The reason why this is the case is the point that initially corresponded to f of 0 now must be at f of c minus c. And so our x assumes the value c where it was initially at the point 0. I hope that makes a little bit of sense. Now, moving on to dilations, we can have horizontal or vertical dilations. When it comes to vertical dilations, we have our function like this, And essentially what happens is we have an a, f of x, for example, and what this will do is it will stretch every single y value outwards by a factor of a. So if we have a scale factor of 2, f of x, then what was initially at 1, 1 will now be at 1, 2, because 1 has been stretched up into 2. Okay? So each y value, essentially, you're grabbing straight at this x-axis, and you're pulling away in both directions. And so each of the y values are going to be stretched out as far as they possibly can. In the case of, for example, y equals 4x squared, we have our point 0. At 1, it's initially at 1, but now it's stretched up to 4. So if we have our initial function like this, what was initially at 1, 1 is now at 1, 4 up here. What was initially at 2, 4 is now at 4, 16. And so as a result, everything's been stretched upwards by a scale factor of 4. And this is what our dilation looks like. In the case of horizontal dilations, we are doing the exact same thing, but in this case, we're doing it in the horizontal direction. If we look at f of bx, for example, this will dilate actually by a scale factor of 1 over b. Because what was initially at f of 1, for example, now has to be at f of b times 1 over b. So what was initially at 1 has now moved to 1 over b. So it's a contraction by a scale factor of b. Contraction by a scale factor b. And so if we look at the function, for example, y equals 2x all squared, then we can see that we have got 0, 0. What's initially at 1 is now at 1/2. What's initially at 2 is now at 1. And so at 2 in our original function, y equals x squared, 2 corresponded to 4, right? And so 1, at the point 1 here now, we have a corresponding y value of 4. At the point 2, the point 2 in our function y equals 2x squared is where our function x equaled 4 initially. And at x equals 4 in y equals x squared, we have y equal to 16. And so we have at 2 in our dilated function, we are corresponding to a point 16 up here. And so we have a dilation up in this direction. And I should also note that 2x squared goes out into 4x squared. And that's no coincidence. In the case of quadratic functions, horizontal dilations and vertical dilations do the same thing. Okay, the last thing I want to look at is reflections. Reflections similarly can be horizontal or vertical, and I'll show you why they would be considered as a kind of subset of dilations in terms of what you do algebraically. When it comes to vertical reflections, essentially what's happening is you are using the x-axis as a mirror. And it looks like negative f of x. So where we were looking at vertical dilations by a scale factor of a, we now have a negative value. And so if we look at our initial function, what was initially, for example, let's say it's this function here, this function will be reflected in the x-axis here, and as a result, it'll be reflected like this. And this is our line negative f of x, and this is f of x. Okay? In the case of horizontal reflections, that will be f of negative x, and this is a reflection in the y-axis, using the y-axis as a mirror. So for example, let's say we have our line y equals x, y equals negative x will then be this bit reflected in the y-axis shifts over here, and this bit reflected in the y-axis shifts over here. And so we have the line y equals negative x, and this is the line y equals x. So essentially you're using the y-axis as a mirror. Alright, last thing I'm going to go over is the distinction between functions and relations. What we're looking at previously is that each value in a domain for a function will map into a corresponding range. So if we have a square, it will uniquely map onto a triangle. If we have a circle, it will uniquely map onto a pentagon. Okay? The main thing is we can't have a square that goes out and suddenly maps over into a hexagon, for example. So for each unique input, we have a unique output. If we have, for example, something like this, we can see, and this is a function, if we say this is y, this is x, we can see that this isn't a function of x because for some specified x value, we'll call it x1, we have a corresponding y value here, here, and here. And so there isn't a unique range that our input maps onto. This would therefore not be a function. In the case of a quadratic though, we have each value of x maps onto one corresponding y value. x1 here maps onto this corresponding y value. And x2 over here maps onto one and only one corresponding y value. The way that we can test for this is by applying the vertical line test. That is, if we put a vertical line anywhere along the graph of the function, it should only ever intersect at one point. If we look at this vertical line test shows we intersect at 2 points. This, on the other hand, only ever intersects at 1 point. So by the vertical line test, this is a function, but this is not a function. So, in terms of functions, we can have a domain mapping onto one and only one range. We have a 1, 2, 1. What can actually also happen is that we have many different things in the domain mapping to the same thing. One classic example is the parabola. In the case of a parabola, we know that -2 maps onto 4, for y equals x squared, and 2 also maps onto 4. The important thing is that each specific input only maps onto one output. So both of these are considered functions. However, if we consider something like a circle, we can see here that a specified x value maps onto two different values. That is, we have one thing mapping to many different outputs. So in this case, we have a one-to-many, and this is not considered a function, it is instead a relation. There's some relation between our variables x and y, but it's not a function. Okay, cool. So we have had a look at the concept of a function. We've used function notation, determined domain and range, recognized independent and dependent variables, had a look at some transformations, graphs of functions, and recognize the distinction between functions and relations, as well as apply the vertical line test. If you have any questions regarding this, make sure you leave a comment. Also subscribe so you don't miss any new videos. I'll be releasing the last video of the functions unit on the 7th of November, so in 2 days, so stay tuned for that. And again, comment if you don't understand a concept or I've missed something, and I'll see you in the next video. Thank you.